Today we're going to talk about complex numbers. So we've talked about number types before, and remember that we have natural or counting numbers, we have whole numbers, we have integers, we have rational numbers, and all of those make up the real numbers. So I'm doing this kind of like a little chart here. So if you knew that a number was natural, like a counting number like 5, it's also whole, it's also an integer, it's also rational, it's also real. So all the number types that we've been dealing with have been of this type. Well, there's also something called imaginary numbers. And when you look at all the real numbers and all the imaginary numbers together, they make up the set of complex numbers. So complex numbers have, actually we're just going to talk about the imaginary component part of that. We use an I to represent that imaginary number, and I equals the square root of -1. Well, think about what that means. That means I squared. If you square the square root of -1, you get -1. So this is our pure imaginary. So we have I equals the square root of -1. But if we have I squared, we can simplify that to -1. And so we're going to make use of that. This is what we're going to deal with when we have a square root of a negative. Now these are used in real life. Electrical engineers use these ideas of complex and imaginary numbers. So we're going to talk about these. So first here we're asked to simplify the square root of -28. Well, we've been simplifying square roots, so we've talked about that a little bit. But the first thing I want you to do is think about this as the square root of -1 times the square root of 28. So we know how to do this. Remember, we look for the largest perfect square that goes into 28. If you are not sure how to do this, you'll want to watch the video I have of simplifying square roots. So we get the square root of 4 times the square root of 7. So this square root of -1 is I. The square root of 4 is 2. And we can't simplify the square root of 7. Now, usually we'll put the 2 in front, and we might write 2I root 7 as our answer. Over here, I'm going to start by thinking of this as the square root of -1 times the square root of 32. So I know it's going to be I root 32, but I have to simplify this. So you're looking for the largest perfect square that goes into 32, and that would be 16. The square root of 16 is 4, so it's 4 root 2, and then don't forget we have to multiply by the I, so I get 4I root 2. Now these are considered pure imaginary. I'll show you, sometimes you have a real component and an imaginary component. We'll see that in a little bit. So you might want to pause the video and try these. I'm going to work them out, but if you want to try them first, you should pause this. So when we think of this as the square root of -1 times the square root of 50, so I know it's going to be I root 50. I can break this down to the square root of 25 times the square root of 2. So I get 5 root 2, so it's going to be 5I root 2. And this one, we are going to think of this as the square root of -1 times the square root of 45. So we know it's going to be I root 45. Largest perfect square that goes into 45 is 9. So I get 3 root 5, so my answer is going to be 3I root 5. So we can multiply. Now remember, I is a number, it's not a variable. But just like you could do -3x times 2x, and you would get -6x squared. Remember, I is a number. It's the square root of -1. It's not a variable, but it works the same way. So we can just multiply this. We get -6I squared. However, we have to remember that I squared equals -1. So anytime you see an I squared, we're going to change that. So it's going to be -6 times -1, which is +6. On part B, be careful that you don't look and say, oh, a negative times negative is positive, because the negative is underneath the radical sign, so you can't look at it that way. So we're going to think of this as, well, since we have the negative underneath there, every time we do, that's going to just simplify to I root 12 times I root 2. So then we can multiply together, and if we multiply I times I, we get I squared. Now we haven't really talked about this yet, but if you have the square root of 12 times the square root of 2, you can actually multiply those together and get the square root of 24. And when we do that, we're going to have the largest perfect square is 4, so we have the square root of 4 times the square root of 6. The square root of 4 is 2, so we have 2I squared root 6. We're almost done, but remember I squared equals -1. So this is a -1 times 2, so we get -2 root 6, and that's our answer. So notice we had a negative answer, so be careful that you don't see these two negatives and think it's positive, because they're underneath the radical sign, it doesn't work that way. So you can pause the video and try these. So on this one, we're going to get 15I squared, and since I squared is -1, we get -15. Here we're going to get I root 2 times I root 6. I don't know why they have the big humongous dot for a time sign. So we have I squared root 12. So we know that I squared is just going to be a -1. And then we can simplify this root 12 because 4 is a largest perfect square that goes evenly. So my answer is -2 root 3. So then how does that impact, like, for solving an equation? So suppose I'm trying to solve the equation 5y squared plus 20 equals 0. This is a quadratic equation because my variable is squared. And it's also one that we would use the square root property because there's no linear term. So to solve this, I'll write down, we're going to use the square root property. So I'm going to subtract 20 and divide by 5. So I get y squared equals -4. Well, remember, like the next step would be to square root both sides. And don't forget, we have to do plus or minus. That still applies. But I've got the square root of a negative. Well, we know the square root of 4 is 2, so we're dealing with this. So because I have a negative underneath the radical, I know I can think of this as I root 4. Well, the square root of 4 is 2, so I get 2I. But I still have this plus or minus. So my answer is plus or minus 2I. Now, if I graphed this, if the related parabola, of course they made this a y instead of an x, but if in that situation, if you got roots of your equation plus or minus 2I and they're imaginary, that would mean that the parabola doesn't cross the x-axis. And I recognize this is not an x, so that really doesn't kind of apply to this one. But so that's how you would do a problem like this. So you might want to pause this and try this. First, you would subtract 50 and then divide by 2. And then next, we're going to square root both sides. And don't forget the plus or minus. So again, and you don't have to do this off to the side. I'm doing this just because I'm making a video and explaining it. But every time you see this negative underneath the square root, we know it's going to be I root 25, which is going to be 5I. So I get plus or minus 5I for my answer. So sometimes, and I mentioned this, you can have a real number part. So here's the real number part and an imaginary part. So the format of that, which they list right here, a plus bi, where the a is the real part and the bi is the imaginary part. So you can have situations like that. Now, these would be considered not like terms. So I can't combine the real part with the imaginary part and say 7 of something. Okay, I can combine real parts with other real parts, and I can combine imaginary parts with other imaginary parts, but they have to be like terms, just like they are with variables. So if I am asked to simplify 3 plus 5i plus 2 minus 4i, it's just like if it's the same strategy of if this had been an x. Again, please don't misunderstand and think that I'm saying that the I is a variable. It's not. It's a number. It's the square root of -1. But it works the same way. So you combine like terms. So because it's a plus, I don't have to worry about the parentheses. So 3 plus 2 is 5. And a 5i plus a -4i is a 1i. So I just get 5 plus I. Down here, I'm going to start by distributing the minus sign, which makes this a plus 7i. So now I'm going to combine 4 minus 3 is 1, and -6i plus 7i is a positive I. Okay, not hard. So go ahead and pause it and you try these. So here on this first one, you would get 5 plus 10i. Here, it's worth taking the step to distribute. We're going to have a plus 2 and a minus 5i. 3 plus 2 is 5. 2i minus 5i, we get a minus 3i. You can also multiply. So when you multiply, you can do FOIL, you can do a box. So if you are going to do FOIL, we do first, outside, inside, and last. And when we do last, we get -6i squared. Now we can combine like terms. The middle two are like terms, so we have an 8i. And then we have to remember I squared is -1. So that means I have a -6 times a -1, which makes this a +6. So now I can combine the real parts. So I get 14 plus 8i is my answer. Go ahead and try the next problem. You might want to pause the video. I'm going to do this one with a box, just in case some of you are doing that method. So we have 3 plus 2i and 3 minus 2i. So we multiply, so we get 9. Here I get 6i. Here I get -6i. And here I multiply, I get -4i squared. Now when we combine like terms, these are going to cancel out because they're opposites. So I get 9 minus 4i squared. But remember, I squared is -1. So when you replace that, that's going to change this sign to a 9 plus 4. So we get 13. Now, notice that I started with complex numbers that had real and imaginary parts, and I ended up with a real number for my answer. And that's because if you notice, we have the difference of two squares here, is the situation. So, and we have that pattern. So these are actually called conjugate pairs. When you have one of them is plus and the other one is minus. And so when you multiply an imaginary number or a complex number by its conjugate, you actually do cancel out the imaginary part and you'll end up with a real number. The last thing I want to talk about is what if you were asked to evaluate I to the 53rd power? And we want to establish some kind of a pattern so we can see what's going on. So remember, if we have an I, we know that that's the square root of -1. I'm not going to list, I'll list that over here. So I squared, remember, is -1. So then if you have I cubed, that's just I squared times I to get I cubed. So that's -1 times I, or we could just say -I. If you have I to the 4th power, well, we can think of that as I squared times I squared. Remember, when you multiply and the bases are the same, you add the exponent, so we can think of it like that. So I squared we know is -1, so I get -1 times -1, which is +1. And for I to the 5th power, I can think of that as I to the 4th power times I to the 1st power, or just I. And I to the 4th power we just showed was 1, and 1 times I is I. So I can think of I to the 6th power as I to the 5th power times I. I mean, there's a lot of ways I can break that down, but we just figured out I to the 5th power is I, and I times I is I squared, which is -1. And I'm actually going to, well, I'll do a couple more. But you should start noticing here. Let me get a highlighter. So we started with I, and then we had -1, and then we had -I, and then we had 1. Then we have I. Then we have -1. Notice it's repeating that pattern. So if we kept going, the next one we would have is going to be -I, and then after that is going to be 1. So that's the pattern. So it repeats I, -1, -I, 1. So every fourth, and then it's going to go back again. So it's just going to circle back around. So I'm not going to tell you, actually I'll tell you the answer. So this one is going to be I, but I'm not going to tell you why. See if you can figure that out, how I know that, using this pattern. And I didn't have to go through I to the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10, 11, 12, 13, 14, 15. I didn't do that. I didn't keep counting all the way up to 53, although you could. But then what if I asked, what's I to the 3,521st power? You probably don't want to go through and count through. So there is a way using this pattern. So think about that.